Great. So it's a great pleasure to have Will Chen from Columbia University today. And Will Chen will be talking about strong approximation for the Markov equation via non-abelian level structures on elliptic curves.
Okay. Yeah. So thanks for inviting me. It's great to be back. Thanks to Peter Sarnak for introducing this problem to me almost 4 years ago at this point. So I'm going to talk about the Markov equation. So the Markov equation is this guy. It's x squared plus y squared plus z squared minus xyz equals 0. So I think, as I understand, this Markov equation first appeared in the work of Markoff in 1879 on his binary quadratic forms. But since then, it's also appeared in a variety of other contexts. So it has some relations to Diophantine approximation, the Markov triples, which are these positive integer solutions. They're related to, I think by the work of Harvey Cohn, they're related to the lengths of configurations of just certain closed geodesics on the modular torus. The modular torus is a quotient of the upper applane by a commutator subgroup of SL2Z. And this quotient is, the action is free, and this quotient is a genus 1 surface with exactly 1 cusp. And it turns out that these positive integer solutions are essentially just the lengths of certain configurations of geodesics. And another place where this equation appears is that turns out that that the affine surface defined by this equation is actually a slice or some kind of level set of a certain character variety. So this is the perspective that we'll take, and I'll explain what a character variety is and exactly which one we're talking about. So in this case, it'll be the character variety for SL2 representations of the fundamental group of a punctured torus. Okay. So when talking about the Markov equation, often there's a certain group of automorphisms which appears. So I'll just call that one gamma. So this is a group of automorphisms generated by permuting the coordinates. So I mean, this is a symmetric equation, symmetric in x, y, and z. So you can permute the coordinates, and it's also so it's generated by the permutations of the coordinates and this additional guy, which is sometimes called a Vieta involution. Okay. And one of the first results that's known about the Markov equation is that the set of Markov triples, so these are the positive integer solutions to this equation, they form a single gamma orbit. They form a single orbit under this group of automorphisms. So this is due to Markov. Okay. So today we're going to mostly focus, instead of on the integer solutions, we're going to focus on the solutions over FP. So to set some notation, x of p will just denote x, the FP points of this Markov surface. X star of p will denote all the points, all the FP points except for the trivial solution, 0, 0, 0. So it's easy. You can sort of verify by I that certainly this trivial solution is a fixed point of this group gamma, and so you'll have at least 2 orbits, right, of gamma on this set, or of gamma on x of p. So you'll have you'll have a singleton orbit. And in 2016, Bourgain, Gabard, and Sarnak, they studied this action of gamma on x of p, and they conjectured that essentially it acts transitively on everything else other than the trivial solution. So there's a trivial solution, which is a singleton orbit, and then there's everything else. And their conjecture is that for all primes p, that this action of gamma is transitive. Okay, so the fact that this action of gamma is transitive actually, it tells you a little more. It tells you that, wait a minute. Okay, cool. All right. The fact that this gamma action is transitive, it tells you that in fact the set of integral solutions must surject onto the FP solutions, right? This is essentially because, well, if you just you just need to check, right, that there is some point, some integer solution which does not map to, which is not just 0 mod p in all the coordinates, right? So it must map to an orbit which is not the singleton trivial orbit, and so that would imply that if gamma acts transitively, then everything else, any orbit in here which does not map to a trivial orbit must in fact map onto the complement of 0, 0, 0, and so this implies that this map is surjective.
So
and in this case,
p equals 3.
Yeah, well, you can find another one. So if p equals, I mean, so you can verify it. You can also verify it for p equals 3.
The way to fix that up is really he should have a 3 there if he's talking about exactly Markov, and then it fixes itself up. But it's a minor point.
That's true. Yeah.
Then you do 1, 1, 1. You mean?
Oh, actually, I guess.
Yeah, then you do 1, 1, 1. That's correct.
Yeah, let's just say p is at least 5. So essentially, every time there's a p involved, you can always assume that's at least 5. Okay, and so following Bourgain, Gambert, and Sarnak, well, they say that this is they call this strong approximation at p. Okay, so I should also mention that this conjecture was actually there's actually a sort of a generalization of this conjecture, which was posed by McCullough and Wanderley in 2013. I think both of them are sort of like low-dimensional topologists, and they posed a conjecture sort of totally group theoretically. And in particular, their conjectures include as a special case this conjecture, and their conjecture was more, in relation to this, so-called T systems that we would sort of briefly discuss before the talk. But anyway, so Bourgain, Gambert, and Sarnak, they worked on this conjecture, and they came pretty close to proving it in an asymptotic sense. So what they showed 2 things. Right. The first thing is, so let E sub BGS, so E stands for exceptional set. So this is essentially the set of all primes such that gamma doesn't act transitively on X star of P. So this is the set of primes where the conjecture fails. Then their first result is that for any epsilon greater than 0, that this exceptional set is essentially very sparse, but possibly infinite. So it's a sparse, but possibly infinite set. So the set where the set of primes where the conjecture fails is sparse but possibly infinite. Okay, and then their second result shows that even when it does fail, essentially can't fail that badly. So what they show is that there's a large orbit, they call it C of P, such that it's essentially everything asymptotically. So in other words, such that for any epsilon greater than 0, then the complement of this large orbit is small. And here, I guess I could also say that X star of P, the size of X star of P, you can actually just count it. It's just P plus or minus 3, according to whether or not P is 1 or 3 mod 4, right? This is like P squared. Okay. So the main theorem that I would like to present today is that, so the first statement is that every gamma orbit on X star P has size congruent to 0 mod P. Right. So that's the statement. There's no, it's not conditional. That's just, it holds for every prime. And if you combine this, right, with their part B, right, so their part B says that if you take, so they expect their conjecture, if their conjecture were true, then the C of P is the whole thing, right? And what part B says is that, unconditionally, the complement of C of P, if you take an orbit which is not some other, hypothetically, if you took some other orbit, which conjecturally doesn't exist, but if it were, if you took some other orbit other than this large orbit, then that orbit must be small, must have size at most P to the epsilon for any positive epsilon, right? So in particular, this says that every gamma orbit has size at least P, and so if you combine these, what you get is that the conjecture can fail at most finitely many times. So EBGS, this exceptional set, is finite. And in fact, you can also check that you can say that it has an explicit upper bound. So there exists an explicit upper bound for the size of the largest prime in this exceptional set.
Is it computationally accessible, this upper bound?
Yeah. So this essentially follows from the proof of BGS. Their methods are effective, and this explicit upper bound was worked out by Elena Fuchs. But her current best upper bound is something on the order of, I think, 100 digits or 1,000 digits. Yeah, so it's not really feasible currently, but yeah, I don't know how much energy she's put. It was just like sort of, her first go through, her first I think read-through of Sarnak's paper, she was able to get this bound. So it's possible that by if you sort of thought about it more, you could get a better upper bound.
You probably wouldn't
essentially
get it down to 100.
Sorry?
You wouldn't get it down to 100.
Oh no, I don't know. I have no idea.
But without a new idea, I think you would need a real new idea. And this has been checked up to a few thousand, I think, by the Cozy Island, who's actually on this. So,
oh, really? So he's checked this for all the
well,
the first 1,000 or so primes?
He can tell you how far he went, I don't know.
Oh, that's pretty good.
It's a fine up to 3,000, he says in the chat.
Nice. Okay, cool. Yeah, so I guess I should also say that McCullough and Wonderly, they also checked it they checked their sort of more generalized conjecture for all prime powers up to like 160 or something. So de Courcy Island, I guess, I mean, he's done a lot more. He's checked it for a lot more. Okay, so the sketch of the argument essentially will go like this. So the first step will show the gamma orbits on x star p are étale geometric fibers of a certain map of stacks. So it's going to be a certain finite flat map of stacks. So by étale geometric fiber, I mean a geometric fiber above a geometric point where the map is étale. So essentially, that means that the cardinality of the fiber is precisely the degree or the size, the degree of the map. Right? So this is going to be an étale geometric fiber of some finite flat map of stacks. This here M1 bar. This is the moduli stack of elliptic curves, the compactified moduli stack of elliptic curves. And so on this moduli stack, there's well-known. I mean, there's a certain line bundle called the Hodge bundle, which we'll call lambda. And you can compute that the degree of lambda is 1/24. Okay, and everything here is like over C. Okay, and the second step. So the point is that that every gamma orbit corresponds to an étale geometric fiber of a map like this, where X, you can think of this as some kind of connected stack, some connected Deligne-Mumford stack. And that this map is finite flat, but it's sort of generically it's étale. Generically, it's finite étale. Okay. Step 2, show that the degree of the pullback of the Hodge bundle is congruent to 0 mod p. Right. So I mean this. Whoops. So this would imply that, I mean, so when you pull back a line bundle on, I mean, these are one-dimensional schemes, right? So when you pull back a line bundle by a finite flat map, then the degree gets multiplied by p. And so if the degree of the pullback is 0 mod p, then at least for p coprime to, for p other than 2 or 3, right? Then this would imply that the degree of f is congruent to 0 mod p. So for p at least 5. So we'll always assume p is at least 5. Which implies a conjecture. Because remember that the degree of f is precisely the size of an étale geometric fiber, which is also in bijection with some gamma orbit on x star of p. Okay. So yeah. So we're going to begin by trying to describe this correspondence. We're going to try to describe the correspondence between the gamma orbits on the FP points of the Markov surface and some étale geometric fiber of some natural map of stacks.
Sorry, could you just clarify, what do you mean by étale geometric fiber?
Yeah, what I mean is that this finite flat map is actually generically étale. And an étale geometric fiber, by that I mean the geometric fiber above a geometric point over which the map is actually étale.
Okay, and sorry, so when you say the gamma orbits are the étale geometric fibers,
are in bijection, yeah. This is sort of you can concoct a bijection between the gamma orbits. So for every gamma orbit, so sorry, I should say every gamma orbit. Show every gamma orbit. So for every gamma orbit, there is such a map, such that that gamma orbit is the geometric fiber of this map above a point where the map is étale.
Okay, thank you.
Yeah.
So wait, so this stack is going to vary not only with P, but also with the particular gamma orbit?
That's right. But I mean, essentially these X's will all be connected components of a certain larger, disconnected stack. And essentially there'll be some, for every P, you'll have some disconnected stack, which is naturally defined. And then each X will be a component.
Yeah. Okay. So the most important thing here is that X is connected, and you will describe X.
Yes, I will describe X. Okay. So X of P as SL2 P representation. So you can think of, so I'm going to describe now how to think of the points, the FP points of the Markov surface as actual SL2P representations, in this case, of a free group of rank 2. And everything here is actually going to hold over any ring R. Okay, so let pi be the free group of rank 2, so generated by A and B. I just noticed my iPad says 9:41 a.m. Tuesday, January 9th. This is strange. So we'll always want to think of pi as the fundamental group of the punctured torus for the rest of this talk. Okay, so consider the functor from R schemes to sets, just given by sending an R scheme T to the set of group homomorphisms from pi. This is just an abstract group to SL2, the group, the group of T value points of the group scheme SL2. Okay, so this functor is sort of obviously representable in the sense that, well, I mean, what does it mean to give a group homomorphism from a free group of rank 2 to this group of T value points of SL2? Well, that's the same as giving prescribing the two images of these two generators of pi, right? And so that's the same. Any such homomorphism is the same as just giving sort of an ordered pair of T value points of SL2. And so this is sort of obviously representable by the functor by the scheme SL2 cross SL2, which we'll call this, the Hom pi SL2, and this is called the representation variety. Okay, so we're actually going to want to, so what I should say really, this title of this section should really be X of P as not just SL2P representations, but isomorphism classes of SL2P representations. So we're going to want to we're going to want to describe every FP point of the Markov surface as an isomorphism class of SL2P representations. The representation variety classifies things not up to isomorphism, it just classifies all SL2 representations of pi. So to get to isomorphism classes, you're going to want to take a quotient. So in this case, we're going to take the GIT quotient of this representation variety by GL2. Right. And in this case, the representation variety is just, it's a very nice affine scheme. And so this GIT quotient has a very simple description. It's just the spec of the ring of invariance. Okay, and this GIT quotient, whatever it is called the character variety. Okay, so it turns out, so I don't know too much about character varieties in general, but it turns out that the character variety for SL2 representations of a free group of rank 2 has an exceptionally simple description. I believe this is first due to Fricke from 1896. I think he did it over C, and the general case over an arbitrary ring was done by Broomfield and Hilden in 1995. They have a book, SL2 representations of finitely presented groups. And what they show is that the map, so if you take the representation variety, you can define 3 coordinates on it, right? So it defines a map to A3 given by sending, say, a T-valued point, which is some representation defined over T, and it sends it to the trace of the image of A, the trace of the image of B. So remember pi, our group pi was generated as a free group on A and B. So it sends the trace, the phi to the trace of phi of A, trace of phi of B, and the trace of phi of AB. And what they show is that this factors through an isomorphism between the character variety. So I mean, certainly it factors through the character variety because these are traces, and in the character variety, you're just taking quotient out by conjugation. What they show is that it factors through an isomorphism between the character variety and affine 3 space. Okay, so that's their theorem. But this character variety has yet another piece of information, and to explain that, it's best to perhaps introduce. So note that the action, there's a natural action of automorphisms of pi on this representation variety. You just take a representation and you precompose by an automorphism, you get another representation. Okay, So this alt pi action also descends to an action on the character variety. So we took the quotient by essentially post-composition, and this alt is acting by pre-composition. So these two actions commute. But then in the character variety, you've modded out by conjugation. So this factors through out pi, an action of out pi, right? And this, of course, factors through the outer action of out pi on pi. Pi here is a fundamental group of a punctured torus, and it's known that for punctured tori, this is the same, out pi is really the same as the mapping class group of the punctured torus. So I'll write the punctured torus as E circ, and this denotes the mapping class group, right? And so this is really an action of the mapping class group on the character variety, and this is how you should think of this action. So the fact that all auto-automorphisms of pi are realized by mapping classes, it gives you an additional piece of information which might not have been obvious before, which is that a mapping class, right, is defined by a self-homeomorphism of the torus up to homotopy or isotopy. And so it has, in particular, it has to send a punctured neighborhood of the puncture to another punctured neighborhood of a puncture, right? In this case, there's only one puncture. It has to send a punctured neighborhood of the puncture to itself by homeomorphism. And so it has to send a small loop around the puncture, a small loop that winds once around the puncture to another small loop that also winds once around the puncture. So it has to send that loop to either itself or to its inverse, right? And in the case of, so such a loop defines a unique conjugacy class, essentially a generator of inertia inside this fundamental group pi. And in terms of our chosen presentation for pi, you can actually write down a representative of this conjugacy class. So if you think of an elliptic curve as given by C modulo lattice, and you take generators for the lattice, then they give you generators for the fundamental group. If you say puncture it somewhere, let's say in the middle here, and you look at a small punctured neighborhood around, if you take a small loop around this puncture, then that's the same as following A, then B, then A inverse, then B inverse, right? So that's the same as the commutator. Okay, so with that in hand, you can define a map from the character variety to A1, which is obtained by sending, you can think of it as being defined from the representation variety to A1, and then it factors through the character variety. So it sends so let's call it tau. It sends a representation phi to the trace of the image of this commutator, right? So this is now well defined. So okay, this is certainly well defined, but moreover, it's actually invariant. It's actually this map is invariant. It's the fibers of the map are preserved by this action of the mapping class group or of out pi. And this corresponds to the fact that in SL2, any matrix has a trace as its inverse. So you can take this map, and via this isomorphism with affine 3 space, you can just transport this map, and you can compute what it is on these trace coordinates. And it turns out that this map transported to affine 3 space is given by x, y, z maps to x squared plus y squared plus z squared minus x, y, z minus 2. Okay, so this is, now you can see the Markov surface appearing. So right, so what this means is that the Markov surface is the pre-image of, so what do we want? We want this to equal zeros, right? So if you set this equal to -2, then you get the Markov surface, right? So it's the pre-image of -2. And moreover, you can also check, this is something that you should check, that the gamma action on the Markov surface, right, is actually isomorphic. It's actually induced by the out pi action on this character variety. So the out pi acts on the character variety, also acts on A3. When you transport its action to A3, it acts on the whole thing of affine 3 space, and in particular restricts to an action on the Markov surface, which is like a level set or a hypersurface inside affine 3 space, and it restricts to the gamma action on the Markov surface. And this is something you can also check. It's you can just take the generators of alt pi, and then you just do some computations. Okay, so this is the first important observation. All right, so remember, we eventually want to get some kind of correspondence between the F2 points of the Markov surface with SL2 isomorphism classes of SL2P representations. So in general, this is quite a subtle business, right? Because I mean, even for algebraically closed fields, it's not necessarily true that the geometric points of a quotient actually correspond to orbits of geometric points of the original space. And of course, for finite fields, I mean, this is even more subtle. But it turns out you can get a good answer here, but you have to restrict your scope a little bit. So let this Hom pi SL2 AI, this will be the subscheme of Hom pi of the representation variety corresponding to absolutely irreducible representations. So in this case, it just means that when you restrict to every residue field, the corresponding representation over the residue field is absolutely irreducible for every residue field. And you can similarly define the corresponding character variety as just the GIT quotient. Okay. Then it's a theorem of Broomfield and Hilden in the same book that, when restricted as follows, that you can actually detect whether or not a representation is absolutely irreducible by looking at its trace invariant. So okay, so I should actually say that this thing here, so this is a function, right? This is basically some kind of number that you can associate to every isomorphism class of representations, and we call this the trace invariant. And the theorem of Broomfield and Hilden is that you can actually detect when a representation is absolutely irreducible just by looking at the trace of the commutator. And the theorem is that the absolutely irreducible part of the character variety is the whole thing minus tau inverse of 2. So as long as the trace invariant is not 2, it's absolutely irreducible. So so I guess you should note that this is 2 and this is -2. So we haven't removed the Markoff surface. At least at least for odd primes, let's say. Okay. So once we restricted to the case of absolutely irreducible representations.
By the way, the case trace 2 is called the Cayley cubic, and that is exceptional in every way from every point of view, and it of course comes up here too. And
right.
because when the trace is 2, then the identity may, A and B could be their identity, right? So well, I guess I'm just pointing there now.
Yeah, so I think also Matthew de Courcy worked out the.
That's the unipotent, yeah.
Yeah. Okay, so at least once you've restricted to the absolutely irreducible part of the character variety, it turns out there is a very good answer. There is a very good moduli interpretation for the F2 points of the Markoff surface. And the statement is due to McBeath in 1969, where he sort of works this out using very explicit equations. He works very explicitly inside SL2. But it's also due to a much more recent work and more general results of Nakamoto in 2000, where he proves sort of very general results, which I'll sort of go over briefly, about character varieties for arbitrary groups in arbitrary degree. And so in particular, what they show is that, so you can take this quotient map, right? Here is a representation variety, this is the character variety, and you can take this quotient map, and the statement is that this quotient map induces bijections, or I guess just a bijection so for every Q, induces bijections between the absolutely irreducible isomorphism classes, GL2Q isomorphism classes of absolutely irreducible representations defined over FQ. They actually correspond to the FQ points of the absolutely irreducible part of the representation of the character variety. And this we know already that this by taking trace coordinates, this is the same as looking at FQ cubed minus the preimage of 2. Okay. So I'll just quickly sketch the proof following Nakamoto. So what Nakamoto.
You're talking about the field with Q elements, right?
Yes. This is SL2 over FQ. So Q is any prime power here, any finite field. So what Nakamoto proves is that this quotient map is so firstly, right, the quotient map is a quotient by GL2. The center of GL2 acts trivially, so it induces an action of PGL2. And what Nakamoto proves is that this quotient map is a universal geometric quotient, and that the PGL2 action is free, and so it's a torsor. So it is a PGL2 torsor. Okay, and so what this implies is that immediately you have a sort of a bijection at the level of geometric points in the following sense. So it means that if you look at SL2 FQ bar AI mod GL2 FQ bar, then this is in bijection with the FQ bar points. This is basically the point that it's a geometric quotient. And this more or less, so it doesn't quite imply injectivity quite just yet, but you need an additional group theoretic input, which is just that you need that two absolutely irreducible representations are conjugate inside GL2 FQ bar, if and only if, well, let's just implies that they're conjugate. Okay. Conjugate in GL2 FQ bar implies that they're actually conjugate in GL2 FQ. Okay. So with that in hand, then the statement that it's a PGL2 torsor implies injectivity. Okay. For surjectivity, what are you asking? The question is it true that every FQ point of the character variety actually comes from is there an FQ point of the representation variety that maps to it, right? But because this quotient map is a torsor, that's the same as saying that the torsor, when you restrict it to the torsor over FQ, is trivial. And it's actually a theorem. I guess I think it's a consequence of the theorem of Lang that all torsors under affine smooth group schemes over finite fields are trivial. But you can also see this by just applying Galois cohomology to the sequence GM to GLN to PGLN to 1. And if you apply Galois cohomology, you'll get some stuff, H1 of, say, FQ, GLN to H1 of FQ, PGLN to H2 FQ of GM. And this first guy is 0 by Hilbert's theorem 90. The last guy is 0 because finite fields have cohomological dimension 1, and so that implies that this middle guy is 0. So all PGLN torsors over finite fields are trivial, and this implies surjectivity.
Do you really need this? I mean, in this case, you know that that every representation is completely determined by trace of A, trace of B, and the trace of A times B, and you know that in the characteristic 0, this is the full affine space. Namely, you can choose A, B, C. You can choose X, Y, Z in any way you want. So you can. So it's a kind of it's a kind of a trivial strong approximation. Namely, you can lift up from FQ to characteristic 0 in any way you want.
Yeah. Okay.
And you get it.
Right.
I think for the case of PGL2, I mean, for the case of
PGL2, yeah, for PGL2 and the free group on 2 generators.
Yeah, that's why McBeath could do all this without that.
Yeah, that's what I the only situation I little bit.
And McBeath does this by hand, yeah, as he said, yeah. You don't need all this. I think he's just showing us.
That's right. Yeah. No, so I'm showing right. So McBeath does this all this by hand. You don't need the stuff from Nakamoto, but the stuff from Nakamoto also allows you to generalize this. So Nakamoto proves this for any degree. So SLN or GLN, you can replace SL2 with GLN, and he also proves this for the fact that it's a torsor. He proves this for any at least finitely presented group. Let's say that. So you can possibly generalize. It's possible that using this together with some additional input, you can actually get congruences for much more general character varieties as well. Okay. So the next point is, so once we have this, right? So what does this give us? This gives us a very explicit sort of geometric characterization of the FQ points of the Markov surface in particular, right? So let's just like revise our notation a little bit. For any element of FQ, let xt of Q be the set of FQ points with trace invariant T. So by the theorem, this is the same as the set of homomorphisms, absolutely irreducible representations to SL2Q, such that the trace of phi of the commutator is equal to T up to conjugation inside GL2. Okay, and let's if you so just as we had x of p in the intro and then x star of p, let xt star of q, let that be the set of points in xt of q, which corresponds to a surjective representation, a representation which surjects onto SL2Q. Okay, and it's easy to check that it follows immediately from the definitions that x negative 2 of p is precisely x of p. These are the FP points of the Markov surface. What requires a little more work, but it's also follows from the results of Beath. He classifies all the subgroups of SL2Q. And it follows from his work that x negative 2 star of p is equal to x star of p from the intro. So the content here is that these two guys are defined in different ways, right? X star of p, these were the non-trivial solutions of the Markov surface, the solutions other than 0, 0, 0. X negative 2 star of p, these are the surjective representations. These are the points, the FP points of the Markov surface that correspond to surjective representations. And the content here, of course, is that the only way for an absolutely irreducible representation of trace invariant negative 2 to not be surjective is if the traces are all 0, 0, 0. That's what it's saying.
But you mean x star? You mean x star with -2 also? I understand. Not all the irreducible one will give you -2 as the trace.
I know, but I'm saying this x star p is the x star p from the very beginning, where it was just the FP points of the Markov surface except for the trivial
I see. Sorry.
Yeah. They're defined in two different ways. That was the right. The notation could be better, I suppose. And again, as before, we have that the out pi action is the same as the gamma action. Okay. So this leads us, so once we have this in hand, right, we have this like very explicit description of the FQ points of the Markov surface in particular. So by this theorem, the FP points of the Markov surface, right, x star p, right, we've established a bijection between this and the set of the set of absolutely irreducible, surjective absolutely irreducible representations with trace invariant -2, right? So that's what we've established. So at this point, we can connect this to a geometric fiber, to an étale geometric fiber of some map of stacks. And the way one way to do this is to consider the moduli stacks of elliptic curves with non-abelian level structures. So just to recall what this means, so let M1 here be the moduli stack of elliptic curves. Here, let's just, we can work over C. Let G be a finite group. For any finite group, you can define this, this pre-sheaf, TG pre, from the moduli stack of elliptic curves to sets. It sends an elliptic curve E over S to the set of G torsors on E. So in this case, E circ means the punctured elliptic curve, so E minus the origin. So it sends E over S to the isomorphism classes of G torsors, essentially, which are only ramified above the origin, so to speak, which are geometrically connected over the base, over S. Okay, and from this, you can also take the associated sheaf, let's call that TG. And by definition, a G structure on E over S is just a section of this sheaf TG applied to E over S. So it's essentially étale locally given by a G torsor, which is geometrically connected, and so on. So once you have this sheaf, you can always construct a stack out of it relative to M1. And because this is a sheaf landing in sets, this will always give you a stack which is representable over M1. So in this case, this is just the stack whose objects, roughly speaking, are just pairs, elliptic curve together with alpha, where alpha is a G structure. So again, alpha is given, alpha is étale locally on S given by a G torsor on the elliptic curve, only ramified over the origin. Okay, so let's now specialize to the case where G is SL2 FQ. Actually, this picture is true for any G, but at least in the case of SL2 FQ, it looks like this. And what you get is you have this is the moduli stack of elliptic curves with SL2 Q structures for any prime power Q. The natural map to the moduli stack of elliptic curves is finite étale, it turns out to be. And you can, a geometric fiber of it is given by essentially this set. A geometric fiber is just going to be given by isomorphism classes of SL2Q torsors on a punctured elliptic curve. And this is naturally in bijection with the surjections from pi. This is by Galois theory. This is in bijection with surjections from pi to SL2Q up to conjugation, where pi here is the pi1 of the elliptic curve, the complex points of the elliptic curve, where this E is now this elliptic curve here. Okay. So because this guy is finite étale, you can understand its geometry by understanding the monodromy action of the fundamental group of the base. So the base here is M1, and this fundamental group is isomorphic to the outer automorphism group of pi, but you have to restrict to the orientation preserving guys. So the way of thinking about out of pi is that it's isomorphic to GL2Z just by looking at the induced automorphisms of the abelianization. Inside here, you have SL2Z, and then out plus is just the preimage. Okay, so the problem is that these, well, I don't know if it's a problem, but one remark is that these moduli stacks, the moduli stacks of elliptic curves with SL2Q structures are generally disconnected. And one way of distinguishing connected components is, well, let's look at two arbitrary points on this moduli stack. And each point will correspond to some SL2Q cover of an elliptic curve only branched over the origin. And you can for any SL2Q cover of an elliptic curve branched only over the origin, you can take a small loop around the puncture or around the branch point, and you can look at the monodromy element that it determines inside SL2Q. Right, and the monodromy around that small loop will determine some kind of a unique conjugacy class inside SL2Q. And then if you take 2 points corresponding to two different SL2Q covers, and if they have different monodromy around if the monodromy around the puncture are different, then they must lie on distinct connected components. So essentially the function which associates to any point of this moduli stack, the conjugacy class in SL2Q given by monodromy around a small positively oriented loop around the puncture, that function is locally constant. And so you can write this as a disjoint union of open and closed substacks as follows. So open and closed substacks, in this case, we're going to take a slightly coarser invariant. We're just going to take the trace of the corresponding conjugacy class of the monodromy element. And this is going to be the open and closed substack corresponding to stuff with trace invariant T. Trace invariant equal to T. And accordingly, there's a similar decomposition of the fiber. This is FQT. And this is FQT is going to be precisely the set of surjections from pi to SL2Q up to conjugation such that the image, the trace of the image of the commutator is equal to T. Okay. So, and then by Galois theory, you can also see that essentially each of these FQT will be precisely the fiber of each of these stacks over M1. Okay, and you can show that it's easy to check essentially that FP -2 at this map. So what is FP -2? FP -2 will be surjections from pi to SL2P up to conjugation inside SL2P, right, with trace invariant -2. That's not quite the same as a Markoff surface, or as the FP points of the Markoff surface, or XP star. But the proposition is that this is 2 to 1, and this is just a simple thing, simple observation. And okay, so that means that if we essentially what we want to show now, right, is that every out plus pi orbit on FP -2 has size congruent to 0 mod P, right? So this is what we want to show. I mean, or at least this would be sufficient, because this compared with this, I mean, the difference is essentially almost a factor of 2, and so as long as P is at least 3, we're good. Okay, so it just suffice to show this. So equivalently, another way of saying this is that we want to show every component, right? This is by Galois theory now. every component of M inside M SL2P -2 has degree over M1 congruent to 0 mod P. Right. This is the same by Galois theory, because the components. So I mean, by Galois theory, the components correspond to orbits of the monodromy group on the geometric fiber, right? And the monodromy group here is precisely this, and the geometric fiber is precisely this. Okay. And finally, this is also equivalent. This is, I guess, more of a technical statement, that this is also equivalent. It's a kind of a technical reduction, that every component of the coarse moduli scheme, can also phrase this in terms of coarse moduli schemes, has degree over the J line, the coarse moduli scheme of elliptic curves, congruent to 0 mod P. Essentially because when you pass from a finite map of stacks, at least over M1, when you pass from a finite map of stacks to M1 to the corresponding map of coarse moduli schemes, then the degree can only sort of differ by a factor of 2. So as long as P is odd, like this is also equivalent. So this is a second key observation.
So up until this point, I mean, the philosophy is that the number of connected components of these moduli spaces, or the connected components, are in one-one correspondence with the, in this case, this action of the mapping class group on the pairs, which is by what you said, the same as the in one-one correspondence with Markoff. Playing devil's advocate, you taking a group theory problem, or if you gave me the geometric problem, reduce it to the group theory problem, then you must solve the group theory problem. But you bring back all this geometry in order to see the congruence.
That's right. Yeah, yeah. So the geometry will appear in the next section. But yeah. So one remark before we continue is
I just want to make clear that this is a very general phenomenon, that the number of connected components is basically describable topologically, group theoretically.
Right. Yeah. So before we continue, I also want to I should make a remark. So like here, this stack or this scheme, it classifies SL2P covers of elliptic curves with trace invariant -2. So we can actually translate this trace invariant condition into a condition on the ramification index. And it turns out that it classifies SL2P covers with ramification 2P. Okay, and it turns out it's this P that appears in this ramification index that gives you the congruence. And the fact that it's 2P corresponds to the fact that essentially anything which appears as a monodromy element of a SL2P cover has to be congruent or has to be conjugate to a matrix that looks like this, where A is actually non-zero. If A is 0, then it can't appear as a monodromy element of a SL2P cover. And so if A is non-zero, then this guy has order 2P.
This is the other unipotent. I mean, Alex pointed out that.
Or I guess you could take 1 even, yeah. Or it's got to be like, yeah, anything which is non-zero at least. Okay, so the congruence. So to explain the congruence, I'm going to first say some things which are slightly wrong, and then, but it sort of I think it makes the exposition a bit clearer. And then we're going to identify where it's wrong, and then identify how to fix it, and then give a precise statement. So we're thinking about the problem now, right? In terms of either of these statements. We want to show every component of M of this moduli stack has degree over M1 congruent to 0 mod P. Okay, so suppose we had, so let M be such a thing, such a component, right? Then it emits a map to M1. And you can look at the universal elliptic curve over M1. And above M, you can take the pullback. And let's say there's, here's the 0 section, here's the 0 section over there. Okay, so now suppose that we had a universal family of covers, so pi over M, right? So we're sort of taught to think that like whenever you have a stack, there's always sort of automatically like a stacky universal family. In this case, it's not quite true, but it's not too far off. And you want to, so this pi should be a connected, the technical term is admissible SL2P cover with ramification index 2p above the origin of the elliptic curve. Okay, and suppose furthermore that we had a section, sigma. Okay, and suppose that this section sigma lies over this section, the zero section. So this is a ramified section. All right, so in this case, what does this tell you? So in this case, we can let's look at the restriction of the cotangent sheaf on E over S, or E over M. And so we have a cotangent sheaf on this guy. We're pulling it back via the zero section. Pulling it back by the zero section is the same as pulling back by pi and then by sigma, right? So that's equal to sigma upper star pi upper star omega of the same sheaf. Okay, and then from here, it turns out that this is isomorphic to, it's a relatively standard calculation, that this is isomorphic to the pullback, the restriction of the cotangent sheaf of C over M, but tensor to the ramification index. And this corresponds to the fact that étale locally, the étale local picture of an admissible cover is like this. So A bracket X maps to A bracket Y. So here's C to E. And it looks like it sends X to the E, where E is the ramification index. And so this induces a map from the conormal sheaf to, sorry, I guess I should say Y, to Y to the E mod Y to the E plus 1, right? And this is isomorphic to Y mod Y squared, all tensor to the E. Okay, so sorry, this here is an isomorphism. And this isomorphism, by sort of a standard exact sequence, this conormal sheaf is isomorphic to the restriction of the cotangent sheaf. This guy is isomorphic to this, and this E tensor, this Y mod Y squared is isomorphic to this. And so that's how you get this isomorphism. So on the other hand, you can also think of this as, this is also the pullback, so sigma 0 upper star. Let's give this some, so let's call this map F tilde, and let's call this map F. So this is sigma 0 upper star F tilde of the pullback of the cotangent sheaf of the universal family over M1. And this is also, you can also pull back a different way, and you get that this is F upper star sigma 0 prime upper star over M1. Okay, so at this point, we've got something which is the Hodge bundle. This guy is the Hodge bundle if M were proper, or if M1 were, if instead of M1, you were considering M1 bar, this would be essentially a Hodge bundle. Or I mean, I guess you could still call it the Hodge bundle, but you can't talk about its degree quite just yet. And if M is proper, so in this case, if M is proper, then we should really be talking about M1 bar here, right? And the degree of sigma upper star of the degree of the restricted cotangent sheaf of C is integral, right? Then we'd have that the degree of the pullback of lambda, right? So this is F upper star lambda. The degree of this pullback will be, so what we know, right, is that the degree of this pullback is a 2p tensor power. If this guy has integral degree, then the degree of the pullback must be congruent to 0 mod 2p, right? But this is also the degree of F times the degree of lambda. And since the degree of lambda in the proper case is 1 over 24, then you get that this implies that the degree of F, actually in this case, you get that the degree of F is like congruent to 48p, but that's, let's just say it's congruent to at least to 0 mod p. Okay, so there are some problems here, right? So firstly, M is not proper. So this is not quite true. That's one problem. Well, that's one problem. Here's another problem. The degree of a line bundle on a stack is not necessarily integral. That's another problem. And the third problem is you don't actually have a universal family. And moreover, you don't necessarily have this section. So it turns out the way to fix this is, so the properness is relatively easy to fix. Instead of considering these moduli stacks as I've done, as I've constructed here, you should instead consider the moduli stacks of admissible. So use ADMG. These are the moduli stacks of admissible G covers of pointed stable curves of genus 1. So use ADMG instead of MG. This is due to Abramovich, Corti, and Bastoli on their work on the stacks of twisted stable maps. And this is also due to essentially there's an essentially identical theory, which is due to Bertin and Romani in a different language. I mean, literally French is a different language, but also like they take a different perspective. Okay, so I'm not going to go into the details on what this stack is or what an admissible G cover means. But the salient, the relevant facts, the relevant properties of ADMG is that this is proper and admits, so it's a proper smooth Deligne-Mumford stack. It admits a universal family. Okay, we also want to relate it to these stacks MG, right? Because we phrased essentially this problem, this conjecture of Bourgain-Yammer and Sarnak in terms of these stacks here. So we want to relate ADMG with MG, and the relation is that inside ADMG, which classifies covers possibly degenerate, right? Possibly singular covers of pointed stable curves of genus 1. Inside here, you have ADM0G, which is the stuff classifying smooth covers. This is the open dense substack, so this is an open dense inclusion. And the stuff classifying, if you restrict to the stuff classifying to the locus classifying smooth covers, then that emits a map to MG. And this map is a gerb under under the center of G. And in particular, this implies that when you induce, when you look at the induced maps on coarse schemes, then it's an isomorphism. So in particular, a gerb is essentially some kind of like a thickening. So it induces an isomorphism on topological spaces, but then all the automorphism groups are now increased, are thickened by, in this case, the center of G. Okay, so the fact that this is one way to sort of make the connection, right? This is why I sort of stated this final equivalence, right? It suffices to just think about the coarse moduli schemes. So here's the precise statement. Once you sort of work all this out and fix all these problems, what you get is this following statement, which is, so let G be a finite group. Let X in ADMG be a connected component, any connected component. And suppose, so the first problem, right, is introducing ADMG has fixed the non-existence of the universal family. It's fixed the properness. What it hasn't fixed is the existence of the section and the non-integrality of line bundles, of the degrees of line bundles. So we still need to fix those two things. The existence of, okay, so firstly, the existence of the section, right? So suppose there is a map from X prime to X. Okay, so let me draw the diagram. So X, let's say X is here. It emits a map to M1. Let's call it F, over, sorry, M1 bar. Over M1 bar, you have E1 bar, the universal pointed stable curve of genus 1. Over X, you have this, again, you have the universal family, which is pulled back. Now, X, remember, admits a universal family. So over X, you have a legit, universal family of admissible G covers. And then suppose further, but the problem is that this map might not admit a ramified section. So this has a section just pulled back from the neutral section on this universal family, but then this map here might not admit a section, or at least a ramified section. And so, but if you can find a base change over which it does, so over X prime, you have, say, C prime, the pullback is C prime to E prime, right? And then you have, it goes like this. And suppose there is a map phi, which is this map, such that C prime admits a section, sigma, over sigma 0, over the 0 section of the elliptic curve. And suppose that the map on core schemes induced by this phi, so this induces X prime to X, right? And this is, we call this phi bar. And suppose this is a finite flat map of degree D. Okay, so this is, these first two assumptions sort of guarantee the existence of a section after passing to some base change. And then this third condition guarantees essentially some kind of integrality condition on the degrees of line bundles. And so the statement is, if the restricted cotangent sheaf of this base change, if when you tensor with some integer m, then it has trivial local characters. So then the statement is that the degree of f bar, so f bar here is the map induced on core schemes, is congruent to 0 mod 12e. Oh, I should say, let's suppose, okay, E is the ramification index. Okay, E is the ramification index. We're assuming that X is a connected component, and so this family has sort of the ramification index on this family is constant. So let's call it.
Can I ask, when you say ramification index,
yeah,
do you mean like the generic ramification index? Or, this is not something it's happening at one point, right? This is something.
It is something at one point essentially. What I mean, right, is okay. So it turns out that this universal family C is representable over X, E is representable over X, and this map is also representable, right? This map. So if you restrict to geometric fibers, you get legit maps of from a curve to an elliptic curve, which is G Galois, and which is essentially generically étal, and then over the origin of the elliptic curve, you have this. You can talk about ramification.
Oh, so you mean over the origin?
Over the origin, yeah. So here, okay. Everything, yeah. Whenever I talk about covers of elliptic curves, I'm always considering covers which are only branch over the origin, and I'm only considering Galois covers, so all the points have the same ramification index over the origin.
Great.
And let E be that ramification index. Then what you get is that if all these conditions are satisfied, then you get that the degree of this map in core spaces is equal to 0 mod 12e divided by the GCD of 12e comma and MD, where M and D are as they appear here and here, right? So M is the one. M is some integer that needs to kill all the local characters of a line bundle on X prime, and then D is just the degree of the finite flat map that you have to pass to get a section. Okay.
Is X prime connected?
Sorry?
X prime.
You can take X prime to be connected. Yeah.
I mean,
it doesn't matter. Yeah. You just take it to be a connected component.
You don't want to be proving the degree of something that's disconnected is divisible by P, because you want to still have this 1-1 correspondence between the orbits.
Actually, I don't think it really matters, because ultimately, ultimately you will you'll always get some congruence on the degree of this composite map, right? And if even doesn't really, so like as long as this thing is sort of prime to P, right? If you show that the composite has to be prime to P, and this is prime to P, no matter whether X prime is connected or not, you'll still get that this is congruent to 0 mod P.
Yeah, if it's
the important thing is that X is connected, I think, perhaps. Yeah, that's the more important thing. Okay, so applying theorem B. So I realize I'm running low on time. I'm just gonna essentially, I have like maybe one half more page, one more half page. Okay, so how do we apply theorem B? So you want to take this theorem where you want to take G is SL2P. Okay, so that's clear. And in this case, right, we're interested in the case where the trace invariant is -2. So that corresponds to, from the previous remark over here, that corresponds to the fact that that the ramification indices are always 2P. And then what we want to show is that we can find M and D such that P is coprime to MD. So coprime to both M and D. Okay. So essentially in this setting, these are the parameters. Essentially, these guys are the parameters that you plug into this theorem B. And you want to verify all three conditions. Okay. So A and B are verified sort of very quickly. So you simply take X prime to be, you can take it to be a component, or you can just take it to be the full ramification divisor. So in this case, maybe I should probably say reduced ramification divisor, depending on what people think of as ramification divisor. You can take it as a ramification divisor of C, of this universal family of, I guess I should say C prime, right? So this universal family here, this is an SL2P cover, so it's got degree, P squared minus 1. Its ramification is 2P. So that means that its ramification divisor, so its ramification indices are 2P. So its reduced ramification divisor will have degree p squared minus 1 over 2. Right, so this is prime to p. So we're good there, right? Because now this guy, it has degree over x, right? So in particular, this means that you can take d to be this. Okay. C, so this verifies conditions A and B. Part C is a lot more subtle. Part C, for part C, essentially what it boils down to is you want to show, it would suffice to show that all automorphism groups of geometric points of ADM SL2 P are prime to P. In fact, we can like restrict to -2, the stuff, the components with trace invariant -2. So we need to show that all these automorphism groups have degree prime to P. Okay, so at this point, this already gives the general idea. So since I'm over time, I'll just state the final result, the result about the automorphism group. So essentially, we've boiled this down to a computation of automorphism groups. And essentially, what are these automorphism groups? So firstly, what is a morphism in ADMG? A morphism is just given by such a diagram. So if this is a G cover and this is another G cover, a morphism here is given by a G equivariant map of the corresponding covers, such that you have such a diagram. So note that such a diagram, the bottom map is induced by the top map because F is G equivariant, and each of the vertical maps, there are G covers, so they end up being quotients essentially. And so what this means is that you have automorphisms of objects in ADMG of admissible covers. Every automorphism of an admissible cover induces an automorphism of the base, right, which is just an automorphism of the elliptic curve, and its kernel, which we can call vertical automorphism groups. So these are the vertical automorphisms. Its kernel is the thing that you want to control, essentially. You know that this guy, the automorphism group of an elliptic curve, this is either mu2 or mu4 or mu6, right? So this is well controlled. So as long as P is at least 3, it'll always be co-prime to this, to all of these automorphism groups. So what you really want to control are the vertical automorphism groups of admissible covers. And it turns out that what you can show is that the vertical automorphism groups of all admissible covers are actually isomorphic to the center. They're reduced to the center of SL2Q. This is this was totally surprising to me. I did not expect such a thing to hold. In fact, like here, you don't even need to restrict to the case of trace invariant -2, and you don't need to restrict to the case where Q is prime. It's true for all, for this stack, for any prime power Q, and no restriction on the trace invariant. And so this implies that you can take, so let's put it this way, all aught groups of ADM SL2Q are killed by 24, right? So you need 12 to kill all the automorphism groups down here of the elliptic curve, and then you need possibly another mu2, another 2 to kill the vertical automorphism groups, because now we know that they're isomorphic to mu2. And so this implies that you can take M is equal to 24, which is okay, because P at least 5, we're good. Okay, so I guess I'll just stop there, and people can ask questions if they want more details. And essentially the proof of this theorem, there are two parts. There's a lot of Galois theory, and then there's ultimately a key computation comes down to, you do a computation on the character variety. And Sarnak, and actually I think this is something that Sarnak already knew. So he already knew that there's this action of rot, right? This rotation guy on the character variety, and essentially on every conic, this action of rot1 acts with orbits all of the same size, and they're sort of at orbits all the maximum possible size. And that fact actually is a key fact that allows you to show that these vertical automorphism groups are all reduced to the center, which is what gives you this thing. I mean, if it just happened to be the case that there was a single vertical automorphism group that had order divisible by P, then you'd be in quite a bit of trouble, and then you'd have to do a lot more work if you wanted to apply this machinery. Okay, so actually before I end, I should say that this idea as presented here, this was actually communicated to me by De Jong. So I had like done a lot of computations, and I noticed that these congruences might hold. And when I asked him, he was like, "Oh, well, I was just talking, I was talking with this other guy, and he told me about this cool connection." And he basically related this stuff. So I'm a bit sad I didn't quite get to think about, I didn't get to come up with this myself. But I guess the danger when you ask for help is that sometimes you get it. All right, so that's it.
Let's thank William for his talk.
May I just ask a short question? You didn't mention at no point now, and I don't remember in what direction it must come up in the theorem of Nielsen, which says that the automorphism group of the free group on two generators preserve the conjugacy class of the commutator. Now, I don't remember if it worked in order to make it well defined, or it works in order to make it transitive. So in what direction?
So that fact arises in this diagram here. So remember, I was talking about how the mapping class group, this action of alt pi, there's a natural action of alt pi on this character variety. That action is reduced. That action is realized by the action of the mapping class group. And the fact that it preserves the commutator means that it preserves the fibers of this map, this trace invariant map, which in particular means that it sort of it acts on, for example, the Markov surface, which is one such fiber.
I see. So that's really the place where Nielsen theorem is hidden behind the screen. Okay.
Yeah.
Yeah. Now I see. Okay. It was.
In your world, that's called the Hickman invariant, Alex,
yeah.
right?
Yeah. I mean, I just remember that when we talked about it like 15 years ago, from my point of view, this was Nielsen theorem, and you called it by a different name. Okay, so now I see it again. Okay, thank you.
Yeah. I have many questions. I suggest that people ask questions, and then it ends, and then those who want to quiz him stay, so that people can go. Meaning this should be like a seminar where at some point you tell everybody who wants to leave. Is 95% of the people.
Okay, so if there are no other questions, I guess we can stop the recording and thank Will again. And if there are further questions, you can stick around and ask Will.